Good morning, everyone. My name is Natan Mish, and today we're going to have a session on data validation for data science. First of all, it's very exciting to be here. After 2 years, we were confined to our Zoom rectangles, so it's good to see faces in person too. Today's session is an hour and a half. It's an interactive session, so feel free to stop me if you have any questions. Just raise your hand, I'll try to spot you, and you can just shout your questions or problems and so on. Take a look at this code gist. Has anyone seen this before? I see a few nods. So this is the kind of error you get if you run even a very basic model, so a random forest regressor with very few features, and your input has null values. So sklearn, for this matter, will shout at you for having null values. And this is something that I've encountered many times. I'm sure you have as well, many of my colleagues. And this is the kind of thing that happens if we don't check our data, we don't validate it before we try to run it or try to fit it. And this is the goal of today's talk, to convince you that the practice of data validation is essential. And I'm also going to show you a few tools that are available in the open source arsenal of Python that you can use for this matter. Some of them are actually pretty cool. So a few words about me. I'm a machine learning engineer at Zimmer Biomet, which is an orthopedics medical devices company. A few years back, I did a master's in social data science at the London School of Economics, and previously I worked at the finance and fintech industries. And another thing about me is that I like finding bugs. I actually love it, and especially if they're my own making. And that is one of the reasons that I went on this journey of exploring data validation tools and actually incorporating in the products that my team is building. And hopefully, I'll show you a good show of them today. So today's agenda, at first I'm going to try to convince you why do you need data validation. And then I'll go over to show you a hands-on kind of like practice of the different tools you can use for different steps in the machine learning or data science lifecycle. It is important to say that I've chosen tools and fit them to steps in the data science lifecycle just for simplicity, but each of these tools that I'm going to show can be also used for different steps. And another thing is that I am focusing in maybe in the way I talk or the way I present it at production systems, but you can also use it if you're running experiments that you iterate on and you run them multiple times. You probably need data validation steps in those experiments too. Even if you have a hobby project that you're building a model in your spare time, and you don't want it to fail when you run maybe a large training job, for example. So you probably need data validation steps there too. What we will not cover is how to optimize your validation holdout data set for deep learning models. The title of this talk might be misleading, so if you were here for that, I won't be offended if you get up and leave. So the 3 notebooks and 3 tools we're going to look at is, first we're going to do validation in databases using Great Expectations, then validation in training pipelines using Pandira, and finally validation in model serving using Pydantic. We might not have enough time for the last one, but all of the notebooks that I'm going to show here and play with are available online in my repository, so you can just clone it, and all of the notebooks are self-explanatory. You can run through them yourselves. I'm just here as a bonus. So instructions for the tutorials. There are 2 ways you can go through it. So either you clone the repository locally and you have your own Python environment and Jupyter installed and use that, or if you navigate to the repository on GitHub, you can just go navigate to each of the notebooks and then click Open in Colab, and then it will open up in Google Colaboratory, and you can run through that. That is if you have a Google account, which I guess you do. So take maybe a minute to navigate to the repository, set it up, see that you have it, and it is all okay. Oh yeah, let's try that. Oops. I can just show you on here. So is this better? Okay, we get it. Yeah, I'll take that as a yes. All right, so let's crack on then. The data set we're going to use for our tutorial is a very famous one, quite common in tutorials and data science training in general. It's on Kaggle. You might have encountered it before. It's the Kaggle house prices prediction competition. It's a data set on houses in Iowa, United States, and different features about them, how much they were sold for, and that's what we're trying to predict. It's simple to use and understand. There's a variety of features, about 80 in total, from different types, and that is useful for our case because that's what we'll be trying to check, different types and so on, and how are we using them. So what does data validation actually mean? So data validation is the practice of checking the integrity, accuracy, and structure of data before it is used. And as you can imagine, data validation is essential not only for data science projects or even software projects in general, but any kind of work that uses data probably should have data validation steps in place. So if you're working in insurance and you have enormous Excel sheets, you probably need data validation. And if you're working in research and you're getting a new batch of data, then you should probably make sure that it is all okay. The kinds of things we can check for when doing data validation are endless. We can validate types, ranges, consistency, and mostly for our data science use case, we want to incorporate the business or the research logic to make our project more robust. How can data become invalid? There are multiple reasons. The first one, which is probably comes up to mind first, is human error. So for example, if you have annotators annotating your target variable, they are more than likely to make one or two mistakes. Let's say in our data set that we'll be practicing, imagine there are people doing the surveys and typing in different things about the houses that we are trying to predict the prices for. And it's not uncommon for those people to maybe add a zero to a house price or maybe leave out a zero. So those are the kinds of like human errors you can do, but obviously there are many, many more you can do. Another thing is outdated or expired data sets. That's something that is fairly common. So for example, in our data set, it is from, let's say a survey comes from 2006, and we are trying to predict for house prices in 2022. And so that might make our model biased. And finally, there can be bugs or changes in upstream data pipelines. So if, for example, you're consuming data in a production system that doesn't come from, that you are not responsible of and you're just a consumer, then there might be a change in that upstream source that you are not aware of, and you should be aware of. And by putting data validation steps in hand, you are more prepared for that kind of scenario. I could go on about this, but I can just let XKCD explain this to us better. So in this cartoon here, there's a few engineers talking to each other, and one of them comes to his colleagues and says, check it out, I made a fully automated data pipeline that collects and processes all the information we need. And his colleague asks him, is it a giant house of cards built from random scripts that will all completely collapse the moment any input does anything weird? And obviously it does. So the reasons to put data validation steps in place. First one, we want to maintain data integrity. And data integrity is a concept when you build software that essentially guarantees the quality of your data. And once you put data validation steps in place in your data science or machine learning product, then you help align that data integrity throughout the whole system. Now, data integrity usually is split into two. So there is the logical data integrity, which is what we actually care about. So that is the content of the data. But there's also the physical data integrity. So if that data, for example, lives in a server farm somewhere, we want to keep it healthy and alive there. But that is not something, obviously, we are responsible for. Unless it's on-prem and it's our responsibility, but that is a different problem. Second is reliability of our system or experiment or project. We want to prevent and detect bugs from the very first interaction with the data. But then we also want to prevent and detect them throughout the data science product lifecycle. We want to minimize the surprises. We want to know what input are we expecting, when are we expecting it, and it can also help us with an early detection of a data drift. So a data drift in data science projects is the concept that when your data set for training pipelines is much different than the data you are actually doing the prediction or classification from. I gave an example earlier. So for example, if your house prices data set is outdated or expired, and then you are trying to do a prediction based on those outdated data points, that might be a problem. Third is readability. We can harness Python's type hints feature for our purposes. So you know how you can use type hints in Python, and I'll show it in the notebooks afterwards to make our code more readable. And that is a very nice feature for these data validation tools and Python working together. Some IDEs will even highlight if you have a problem with the types you are sending back and forth in between functions and classes and so on, which is really nice. Fourth is familiarity. So by implementing validation steps, it will force us to get to know our data better. And as data professionals, we are expected to know our data. And when we are putting in place these data validation steps, then it will force us to look at them, look at the types, look at the different limits, and then know how our data looks like. Some of the tools I'm going to show here even have features for automated data catalogs and data documentation creation, which is really nice. Yeah, so that was familiarity. And now a question for you. So at what point in the model lifecycle should we implement data validation? And this is a very simplistic kind of like diagram of how machine learning or data science product looks like. So where would you think we should put data validation steps in place? Anyone? So I argue we should put data validation steps in all of these places. Pretty much everywhere. So from the very first interaction with the data, at the data ingestion step, we want to make sure that the data we are consuming is what we expect it to. But then also when we are doing data preparation, which you can also call feature engineering, we are manipulating and changing the data. That is the definition of that step. And we want to make sure that when we are doing that, we are not breaking anything and that everything will work as expected. Then in model training, we are passing the data, let's say maybe through a few neural networks. We want to make sure that through each of these steps, the data comes in and comes out as we expect it to, and there are no surprises. And finally, and the very last bit, when the model gets deployed, let's say we are serving a prediction or a classification, when we are getting a data point and we are supposed to make a prediction for that, first of all, we want to make sure that that data point is as we expect it to, as the model expects it to be. But also, when we make that prediction or classification, that the prediction is in the structure that we have defined. So now we will start with the hands-on tutorial. Before I jump in, are there any questions about anything I have just mentioned? No? Okay. All right. So you can all see my screen, right? So for those of you using Colab, you can just navigate to the notebooks here, and you can open in Colab by clicking this here. And this will present the notebook. Did you all get to it? Is it working fine? Yeah? Okay. So first thing we will do is install the required packages and import them to the notebook. So by running this cell here, you can authorize this notebook. I guarantee I have not put any SQL injections there. Yeah, that's true. So this will install the packages we need, and then after it has been installed, we'll import the required packages into our notebook. Okay, cool. It might ask you to restart the runtime to get the packages in our kernel. Once you do that, you should be able to import the packages. All right, and we can crack on. So Great Expectations is an open source tool. It's named after the famous 19th century novel, and I guess that's also where this lovely picture comes from. It's a shared and open source package for ensuring data quality, and it helps us eliminate pipeline debt through data testing, documentation, and profiling. So it is a great tool that you can implement, as I've said before, at any step of your data validation journey and at every step of the data science product. And what's really nice about it is that it has many useful integrations with tools you are probably already using. So it can be connected directly to SQL databases, Apache Spark, Airflow, BigQuery, and many more. But you can also implement it on file systems. So even a local file system, if you have it locally on your local machine, or Azure Blob Storage, Data Lake, GCP Bucket, and so on. With Great Expectations, there's quite a steep learning curve with all of their different terms. It's okay, I'm here to help you with that. We'll go through it hand by hand. There is this dictionary here. We won't go through all of these terms right now because they'll just mean nothing to you. But as we go along and we set up Great Expectation in our project, we will encounter them, and then I'll explain each and every one of them and what they mean. So the first thing we want to do is create a data context. Well, and the data context is essentially the first step in our Great Expectations journey, and it will hold all of the definitions and all of the configurations for Great Expectations in our project. When you run this cell right here, so this will initialize Great Expectations data context, and it will create locally this folder here. So this folder will hold, first of all, the configuration for our project, but it will also hold the expectations, which we'll go over later. Those are the actual assertions and logic that we are putting in place for our data. The checkpoints, which we'll also go over, which are the specific points and the definitions of how to do them and when to do them of the data validation process in place. And many more things. We won't go over all of them right now. I think I've covered the most important things. This is another explanation for what happens in that directory. And there's this nice diagram from the Great Expectations documentation, which shows actually what is in the data context and what we have there. So we'll go over each and every one of those things. So don't you worry. First thing we're going to do is create a data source. To do that, the first thing we'll do is get the data context we have just created. And now we will script a YAML file that will create a data source. So obviously you can do this here in a notebook, but you can imagine that in a production system it will be like a shell script or something more fancy. But to make it more simple and for all of us to understand, I broke it down into different cells in the notebook. So first is the data source name. And what is a data source actually? A data source provides a standard API for accessing and interacting with data from a wide variety of source systems. And an easy way to think about it is that in a data context, you can have multiple data sources. For example, in your project, you might be consuming from a SQL database, but you might be also consuming from a file system somewhere. And by defining multiple data sources, you can handle all of that within the same data context. Next, we're going to define the execution engine. So for Great Expectations to actually perform all of these checks and all of these computations, there needs to be an engine underlying doing all of those computations. And here I've defined a Pandas execution engine just because it's the easiest tool, and I'm sure that all of you, if not most of you, know it. But alternatively, you can also use a Spark execution engine if your project is PySpark oriented, or you can use a SQL Alchemy execution engine if your project is SQL oriented. Moving on, we're going to define a data asset and the data asset name. And a data asset is a collection of records within a data source, which is usually named based on the underlying data system and sliced to correspond to a desired specification. So, for example, in our data set, which is comprised of different surveys for houses and their prices throughout different years, we can say that there were multiple surveys throughout many years, and one data asset is one survey from 1 year. So the hierarchy is we have multiple data sources, and for each data source, we might have multiple data assets. Next, we're going to define the data connector. So the data connector provides the config details based on the source data system, which are needed by a data source to define data assets. Quite a mouthful, but what essentially it means is how do we connect to this data asset? And that's what we're doing here. What we will then do is combine all of these configs into one dictionary, which is this dictionary here. And we will script that dictionary into a YAML file. And Great Expectation provides this nice method called test YAML config, which actually makes sure that your YAML configuration is okay and you didn't do anything wrong. So running that will tell us that we will successfully instantiate a data source. We haven't really added it to our project yet. And to do that, we'll run this cell, which is add data source, and we'll add our data source config to it. We can see that it has been created successfully by running this cell, and congratulations, you have now got a data source in your data context. Next on comes the real core of Great Expectations and the thing we are actually all here for. So creating a Great Expectation suite. And an expectation suite is a collection of expectations. What is an expectation? It's an assertion about our data. And once we will see some of the examples, it will become more clear. So how do we actually build or write or define our expectations? There are multiple methods. Again, thanks to the great guys at Great Expectations, we have this diagram here that shows a few ways you can do it. So one way you can do it is by looking at the metadata and then creating custom scripts. You can also use your own domain knowledge. So if you're already aware of the data that you're working with and you know the different limitations, or maybe you've even been instructed what are the limitations, you can just straight ahead write config JSONs and add them as an expectation suite to your project. Another way you can do it is by using profilers. So Great Expectations offers automatic profilers that look at your data, runs through them, scan them, and then gives you all of the different ranges, types, and basically conclusions it reaches from the data. What we'll be doing is a bit of both. It's introspection. So we'll be going in the notebook, looking at the data as we work through it, and then building expectations from it. And in this way, we'll create an expectation suite. So first step would be to read in our data file for our matter, and this is using this read CSV method right here. It will go to the repository, pull that file from it, and just read it in. And this will be Pandas data frame for all sorts of matters, but it will also have on top of it a few data expectations properties and methods that we're going to use. In the same way, you can also use read Excel, read table, Parquet, and so on. So let's take a look at our Pandas data frame and see how it looks like. So as you can see already, there are many different features. And obviously, each and every one of these features will have its own limitations and things we should be aware of. So the way to actually see what expectations you can already put in place is if you're in a Jupyter notebook, if you go to this cell and then you put your cursor here and then you press tab, it will open up all of the different expectations you have. But if you're in Colab like me, then you can you can do something like this, and then it will list all of the different methods and properties this data frame has, and we can see already all of these expect methods. So you can see expect distinct values to be in set, expect most common value to be in set, and so on. And this lists all of the different checks that are already built in Great Expectations that you can just use out of the box. And what's really cool about Great Expectations is that you can also build your own custom expectations and use them in your project. Not only that, you can upload your your custom expectations that you've built into this public repository of expectations here. And it won't load right now for some reason. Oh, it's still loading. But you'll see here there are many, many more expectations that were crowdsourced essentially. And there are many, many cool ones. For example, I saw a few days ago, there is an expectation for a column that holds Bitcoin wallets to make sure that that Bitcoin wallet actually exists. So it goes and it interacts with the API, checks that that Bitcoin wallet exists, and that way it validates And that is the expectation, essentially. So let's create a few expectations. First one is quite straightforward and easy. We expect the ID column in our data frame to exist. So by running this cell right here, it will run this check, it will run this expectation. It won't add it to our project yet, but it will make sure, it will validate that it is actually valid for our data frame. And you can see this flag here, success equals true, which means that this is valid for our data frame. We can also add an expectation called expect column values to be unique, and this will check that all of the values in our column are unique. Another useful thing is that it shows how many values it had actually scanned through, how many of them were missing, and then if there were any unexpected values, it will count them here and show percentages and so on. But what happens when an expectation fails? So let's look at that. In this one, I have defined the column max to be between 0 and 100,000, which I know doesn't hold. Let's see what happens when I run that. So if I run that, it will first of all say success equals false, but it will also tell me what was the observed value that made this expectation fail. And as you can imagine, this would be really useful in a production system if you want to know what caused your expectation to fail. Few other useful expectations. So we can expect column distinct values to be in set. So we run this. It will show you the actual values that were observed. So this column here is actually a string column, but from looking at the data here, we can actually know that it is expecting these only these values here. And I guess if you're working with the data, you will know that this is kind of a zoning feature, and there's a zoning category, and these are the expected values and accepted values. We can see this was successful. Moving on, we can also expect the column mean to be between a range, in a range. So we can also add that, and it will tell us what that mean actually was. So after we've ran all of these expectations, what Great Expectation can do is that it can collect all of these expectations into an expectation suite by running this method right here, get expectation suite. And you'll see that it has collected all of the successful expectations we have just ran, and will put them together in one expectation suite. Those that have failed, it will leave out. And also, if you've had duplicate expectations, it will also leave out the duplicates. If you do want the failed expectations to be in your expectation suite, there is this keyword here that you can use, discard failed expectation, and you can use that. To add that expectation suite to your data context, you'll use the save expectation suite method, and we'll call it my expectations. And by running that, it will add this JSON file to our Great Expectations directory. And that is that about expectation suite. Are there any questions at this point about any of this?
Can you get the index of the rows that failed?
Yes, I believe so. I don't remember it by heart, but I've seen it before. Yeah. Anything else? No? Okay. So we will do a short exercise, and this is not any test or quiz, don't worry. It's just for you to play around with the Great Expectations yourselves. So there are a few definitions here, a few expectations that you are asked to put in place, and you can put them here. And just play around with it and see if it works for you. Not all of the expectations that you are asked to put in place here were mentioned in what I just showed, so you'll probably have to find them in the expectations directory, which I've just showed you in the Great Expectations website. So take a few minutes to do that. Let me know if you have any questions or any trouble. And yeah, let's take about 4 minutes, let's say. Yeah. Yeah, so we will show later what you when you compare that and then it gives you a summary of what went wrong. I will show that in the next exercise.
Yeah. So mine really probably suffering from
Okay, how is it looking? Did anyone encounter any issues? No. This is a friendly reminder to drink water. Today is supposed to be the hottest day in London since I've moved here, essentially. So, very important. Okay. So it looks like there were no great issues. Otherwise, other than the Great Expectations not really working on M1 with Conda Forge, which is unfortunate, but M1 has its limitations, we all know. So let's look at the solutions, and if you go to the GitHub repository and you look at the notebooks directory, there is exercise solutions here, and these are the solutions for this exercise right here. So to check that a column is of type, you just expect column values to be of type. To check for null values, you expect column values to not be null. Column min is defined this way. If you want to define a column median, it's this way. And the last one, which might have been a bit tricky, is expect most column values to be in set. So if sale type is a type of categorical type of column, and you have multiple categories, so you define here what is the set from which the most expected value should be in. Any questions about that? No. Okay, cool. So moving on, and the last bit in this notebook here would be to actually validating the data in a data checkpoint. And a checkpoint is the primary means for validating data in a production deployment of great expectations. So a checkpoint can be put in multiple places, as I've mentioned before. So you can put it at a data ingestion level, or at the training pipeline level, or at the serving level. But let's say we are doing this for a database, and we are appending a data batch to our database. We'll call this checkpoint data batch appended. And then we are defining the checkpoint in this way using this config. And we'll use the same definitions that we've used before. So you remember how we defined a data source. This is the data source we're going to use. We've defined the connector and the asset, data asset. And so these are things we have defined previously. Now we're going to use them in a checkpoint. And it also asks us which expectation suite to use. And we're going to use the expectation suite we have just created. So running this cell will add a checkpoint to our data context project. It will still not run the checkpoint. It is just a definition of how to run it. As you can see here in the object it returned in this dictionary, it has an action list. What are the things it's going to do when it runs this checkpoint? So the first thing it will do is it will store the validation result. It will run through the data, scan it, and all of the output from it, the result of that scan, would be stored. It will also store the evaluation parameters, all of the things that we have just defined, and it will also update the data documentation. We won't have time for it in this tutorial here, but I really recommend looking at the Great Expectation Data Docs feature. It's a really nice feature that creates a data catalog automatically from your data. So, to run this checkpoint, we'll load a different file, another file, so the home data test file, and we will run the checkpoint on this file here. So, running this cell will create a batch identifier, and batch identifier contains information that uniquely identifies a specific batch from the data asset, such as the delivery date or query time. And running this, you will see that this little progress bar here that shows you how far it has gone along in calculating the metrics. And it will return the result object, which you can then later look at and see what are the results for this checkpoint. So looking at the results object, we can extract the statistics for this checkpoint and for this batch, and we can see that it has evaluated 4 expectations and all of them were successful. But you can also look at a specific expectations and see how it looks like, how the scanning for that expectation, what are the statistics for that. So running this cell, you will see that for this expectation, that if you remember, we've defined a specific category and we've defined it to have a certain set of specific values that it can hold. It has counted how many occurrences there were in this data frame of each of these values. But how does data checkpoint that did not succeed look like? So we are going to create basically a bad data column. We're going to inject a duplicate value into our ID column. And this will basically make our data frame invalid, because remember how we defined before that we are expecting to see unique values for the ID column. And we will define this checkpoint same way as we've defined the other one. And we will get the results. Looking at the statistics, what we will see is that one of these expectations was unsuccessful. And looking at the specific statistics for that specific expectation, we can see that it comes with this useful information that it tells us how many unexpected values were found and how many and what were those values actually. So we can see that this value here, that was the one that caused trouble. And obviously it did not succeed. Any questions about that? No? Cool. All right, so we'll move on. And now we're progressing. If you remember the diagram I showed, we're progressing in the data science life cycle or machine learning life cycle, and we're going to perform data validation in the training pipeline. And for that, we're going to use a different tool, which is called Pandira. Has anyone heard of Pandira, out of curiosity? See 1, 2 hands, maybe 3. Yeah. Yeah, it's, I think from all of the tools in this tutorial here, it's probably the least known one, but it's immensely useful, and my team has implemented it successfully, and we are very happy with it. Obviously, as any kind of like young or not that well known open source tool, it has its limitations, and but it works for us, and we love it. What is good about Pandira is that it integrates, it's built upon Pandas, which is a common tool for all data scientists. And the data scientists in my team, they use Pandas quite a lot, as you can imagine. And Pandira is just a really, really neat, natural integration for doing data validation in their training pipelines or in their experiments. I hope you navigated to this notebook here and installed all of the different tools we're going to be using. Then we're going to import them into our notebook. We're going to read in the data. And first thing we will do is try to train a basic model. And we're going to use the most common like scikit-learn tools for that. So we're going to create a pipeline. For that pipeline, we're going to create a custom class that chooses features. And for this example, we're just going to pipe that choose features column into this pipeline here. We're going to choose these feature names. I've chosen them just because they're the most simple ones and will be useful for this demonstration. So we'll define this pipeline. First step would be the feature selection. Second would be a standard scalar that you're probably all aware of, and it's quite common in these types of pipelines. And then finally, a random forest regressor. The choice of model was arbitrary. It was just for the purposes of demonstration. So then, once we've defined on that, if we try to run this pipeline here, it will scream at us saying the input contains nulls, which, as we've seen before, is something we are trying to avoid. And the tool that will help us with that is Pandira. And Pandira is provides a flexible and expressive API for performing data validation and data frames. It has many useful features. Some of them are, it can perform hypothesis testing, so not only just checking like basic things as we've seen before, so types and ranges and so on. It can also perform hypothesis testing. It has, you can use function decorators to implement it in your pipelines to make it more readable and less heavy on your code. It is using the Pydantic style syntax, if you've seen that before, which helps with readability, and many, many more things. So moving forward, let's start working with Pandera and see how it looks like. So first, let's add another feature to our features and create a Pandira schema. And this is how it looks like. So this is a very, very basic schema for our training data. And what we are defining here are two columns or two fields. One of them is an integer and the other is a string. Obviously, we'll have more, we have more features in our data, but just to show the very basic schema, this is how it looks like. And when we run this validate method on our data frame using this schema, it will validate that what we are serving it is actually, it actually confirms to this schema. So running this will do the validation, Pandera does the validation, and it returns a data frame, which means it has succeeded. Now, as I've mentioned, there are more features here. And we'll see in the rest of the notebook that there is a way to say, check that only these features are or columns are in the data frame, but there is also a way to say, I expect these features to be in, but if there are more, then it's okay. And this is actually the default behavior that you see here. So we've only defined two, so it checked for those two, but there were more features or there were more columns which it basically ignored. And the way you can define these types for the fields or the column, you can use multiple different ways. So these are some of them. You can use NumPy data types, you can use strings, you can use Python types, and so on. But what happens if there is a bad data schema or a schema that doesn't fit your data? So we're defining here. Notice how one of them is different from before. So before we've defined lot config to be a string. Now we're defining it to be a float. And this will throw an error. So Pandira raised a schema error saying expected series lot config to have float 64, and it got an object instead. So besides checking for types, you can also check for ranges, and you can also check, say that a certain field or a certain column is not nullable using this flag here. So running this, it will check for these ranges here. And once we see we get a data frame back, it means that this check has passed and it's all okay. But what happens if you want to catch the bad data? So for example, you run a checkpoint, you run this check against a certain data frame, and some of the values were not what you expected. So you want, in a production system, what you would want to do is probably not make the system break and stop, throw an error like we've seen, but you want it to continue, isolate that data that we saw, put it aside, and then continue with the rest of the data. So to do that, we're going to take a sample of the data just to make it easier and define this bad data schema, I call it. And in this schema right here, year built, I've defined it to be in the range between 1900 and 1990. And obviously, in our data set, we have houses that were built before that. So this will, if Pandira will check it, it will throw an error. And here, this is how it happens. As you see here, it says that this check has failed, and these are the failure cases. And to overcome this, we can use a try except block to catch that bad data. And a try except block is actually a common practice in Python. It might not be so common in other languages, but in Python it's actually okay and it's encouraged. It follows this concept called EAFP, easier to ask for forgiveness than permission. And by using that, we can isolate the failure cases into a failure cases data frame, and this is how it will look like. So we get the column year built. This is the check that has failed. We get the failure case, which is the actual value that made the check fail, and we also get that index. And by using that, we can create a filtered data frame with only the accepted values that we are accepting. And once we run the validation on that, we can see that we're all good. Did that make sense? Yeah? Okay, cool. As we've seen before, we can validate acceptable categorical variables. So let's say we've defined accepted values for lot config. We run this. We define this PA check is in these values, and that will make sure that the values in this column are only from this set. And we see that we have a schema error because we haven't added this value to our set, as you can see here. There are many other useful methods in this check class. Some of them are listed here, but not all of them. And you can go on the Pandira documentation website, see all of them. It's you can probably find a few that will be good for your use case. Moving on, we can use a flag called Coerce. So let's say we have this field in our data frame called lot area, and it's an integer. And we can use this Coerce flag to basically tell Pandira whether to force the type we are defining on the data, if possible, or not. So we are defining lot area to be float, but we're setting Coerce to false, meaning don't force it on the data. And running this validate method will throw an error. But if we do the same using Coerce equals true, it will force the float type on an integer type if possible. I'm not saying this is good practice, I'm saying that it's possible. And another useful fact is strict. So you remember how I mentioned before, you don't have to define all of the fields or all of the features in your schema. You can define a few of them and have Pandira only check for those you have defined. But using the strict flag, you tell it to make sure that only the fields that you have defined are in that data frame. So you can either use strict equals true, but you can also use strict equals filter, which what it does is that if there are any other fields in your data frame, it will filter those that are not defined in your schema. And this is how it looks like. Any questions so far about Pandira? Yep.
Why would I want to use Pandira over Great Expectations? Why do I need both?
That's a good question. I think it's a matter of usability and your team or yourself who use the tool. So we found that the data scientists in our team are picking up Pandira more easily. And I think that was the main reason. Also, you might consider using a tool which has a bigger community. So for example, Pandira I think it probably has a smaller community than Great Expectations. So if you want something that is a bit more reliable, then I would say go for Great Expectations. But as I've said before, we use Pandira, we love it, and it's in our production system. Things to consider. Any more questions? Yeah.
Compared to Great Expectations, Pandera doesn't seem to have any validation or distributions, right? So it doesn't give you anything on the mean or the median or stuff like that. It's all row-wise.
So I think you're right, but what you can do is hypothesis testing. So we won't go over this in this notebook here, but using hypothesis testing, for example, let's say you have a column that is called gender in your data frame, and you want to validate that the male and female gender are somewhat distributed in an equal way in your data frame. So you can use hypothesis testing for that. Does that make sense? Yeah. Any more questions? Yeah. Sorry, I couldn't hear that.
Can this be included as a step in the pipeline?
Yeah, so the way my team is including that as step in the pipeline is in the feature engineering steps. We include Pandira decorators that validate, let's say if you have a function that does some kind of feature engineering step, that anything that comes into that function is of a certain schema, and anything that comes out of that function is a different type of schema. Yeah?
If you have very large data sets, do you prefer one language over the other? Let's say millions of rows.
It's a good question. Yeah, obviously, not only in Pandira, Pandas also is known to handle larger data sets, not as well as other tools. In our use case, our data frames are not that big, but if they were bigger, then yeah, we might consider using something else. Anything else? Okay, cool. So we have a short exercise here. Yep. Just to practice defining data frame schemas using Pandira and how to do that. So there are a few definitions here that I ask you to try to write in a Pandira schema. Some of them we've gone over here, but not all of them. You might have to go to the documentation for that. The very last one is a bit harder, so that's a bonus if you want to try it. But let's take, yeah, as before, maybe 4 minutes to try and do that. And if you have any questions, then let me know. Okay, how's it looking? Did it make sense? Let's see. Let's look at the solutions to the exercise. Okay, so this is how the solutions look like. So we're defining the ID column to be an integer. It is required, it is not nullable, and it has to be unique. Then the zoning field, as we've mentioned before, it has to be one of these values, and so on. Checking for range looks like this. Checking for string length looks like this. And the rest of them are pretty straightforward. The one that was probably a little bit harder is this checks one. So notice how these are checks that you run for each column. Well, let's say you have a check that you want to run for multiple columns, as we've defined here. So the first floor square feet and second floor square feet columns, on average, the values of the first floor square feet should be greater than the second one, which makes sense. If you think of a house, usually the first floor has more square feet than the second one. And to do that, you run this checks, you add this checks value here, which is outside the columns definition. And in here, you use a lambda function to check for the mean, and you define it to be less than the mean of the first floor square feet. Okay? All right, so we have 15 minutes left. I think we'll start with the third tutorial, the third notebook. We won't have time to finish it, but for any of you who want, you can just pick it up after. All of the notebooks are pretty self-explanatory. And also, this is probably the most commonly used tool out of the three. So this is using Pydantic to check for data in model serving. So data validation in model serving. And yeah, just out of curiosity, how many of you have heard or used Pydantic? Yeah, quite a lot, yeah. So the first step would be authorize this notebook and install Pydantic. And while it is installing, just so we're on the same page, what do I mean by actually model serving? So this is, again, a very simplistic diagram of how a machine learning or data science product will look in production. So we have the training pipeline, which we've shown before, and we've put data validation steps before in there. We package it up into a model, which is a pickle file or a nonix file or any kind of other type of format that you're using. And then we are handing it over to a serving or inference layer. And in this layer, what you have is either a virtual machine or a Lambda function. You can have it as a Docker container in Kubernetes and so on. But what happens in this layer is that this interacts with the outside world, for that matter. So you have an application, or you have someone triggering this inference layer using an API. So it sends some data using an API to this layer, and then in the serving layer, it sends back the output, so the prediction or classification, and so on. And what we want to check is that whatever comes in here doesn't mess up our model. And that's what we're going to use Pydantic for. And Pydantic, as I've said before, is quite a popular tool. A lot of great projects you're probably already using have Pydantic in them integrated. Even the Jupyter project is using Pydantic. So yeah. So we'll start by reading in a data frame, and we'll choose the features that will come in to our model. And usually when we get this type of file in through the API or this data batch, it will come up as a JSON file or a text file or a CSV file. And for our purposes here, to make it as simple as possible, we're going to mimic it as a JSON file. So this dictionary right here. And this is how it looks like. And as you can see already here, we have a null value, which, as you've seen before, will probably cause havoc in our model. So the way you define a model, so the very basic building block of Pydantic is a model. And in a model, you define an object and how it looks like, and you put all of your checks and validations onto that model. So we create this class by inheriting the base model of Pydantic, and we call it input. Just means this is the input to our model. And in here, we define all of the fields that we are expecting in this input. So those are all of the fields that you've seen before. And we can use this input class to create an input object from the object we are mimicking, so the object we have created earlier. So we are instantiating it in this way and assigning all of these values to it. And this will be our model input object. And already, as you can see, it has thrown an error because there was a validation error on the lot frontage field. So the value is not a valid integer. As we've seen, it is null. So let's say your model can actually handle null values, and it's okay, and you're allowing it, and you know how to handle it. So one of the nice features about Pydantic is that it incorporates the native typing module from Python. So you can import these classes here, optional and any, and you can define that lot frontage will actually be any kind of value, and it will be optional, meaning it can be null. And then we can define this object as before, but a simpler way to do it, instead of defining each of the fields and putting some value into them, you can use this double star syntax in Python to unpack a dictionary and just insert it to the model. And once you've done that, this is how your input object looks like. So a few other cool features from Pydantic is, first of all, you can use recursive models. So you can use a model you've defined before and incorporate it in another model. So let's say we have an input batch, which is a bunch of inputs coming in together at the same time. We are defining it as a list of inputs. And let's say we are creating this dictionary of multiple inputs. Then we can then iterate over that dictionary and insert all of it into an input batch, which will look like this. Another useful feature is enums or enumerations. So you can define a model, so a Pydantic model, that has a set of predefined values. And if you remember this MS zoning feature from before, you'll remember that we have a specific set of values that we allow for this feature. And by defining this MS zoning class using enums, we can incorporate it into our model in this way. And now, moving on to something a little bit more complicated, but is very useful, is custom-based models. And this is based on a problem that we have encountered in our production experience in my team, that the fact that we were able to create custom-based models helped us overcome that problem. So the way to access certain fields or certain values in a Pydantic model or a Pydantic object is by using this dot notation like this. And what happened to us is that we were consuming data that was coming in from a source that we had no control of. And we were expecting one of the field names that we were consuming to be of a specific name. And at some point, after we have built an entire system, that name was changed. And what that meant is that we were using these dot notations in multiple different places. And what that meant is that we had to basically do a huge find and replace across multiple repositories, multiple projects. And yeah, it was a bit of a waste of time, honestly. And the way we decided to overcome this, if this ever happens again, is by using this extended base model. And we've inherited from the base model and added these two methods to it. And what that meant is that not only we can use the dot notation, but we can also use a bracket notation. So let's say we want to access this year built field in our object, we can just do this now with a bracket notation. And what we then added is a class for field names. And in here, we have defined what are the field names for each of our objects. And then whenever, let's say if a field name changes in our upstream source ever again, we only have to change it in one place and not in hundreds or thousands of places. And then we can use it as such. As before, we can catch bad data, as I've shown in Pandira. So let's say we have this input class, which is, again, it's a bad one. It doesn't fit our data. It will break probably if we run it in production. We can incorporate the same try except block that I've shown you before based on this Python concept that I've mentioned. And we can show, first of all, what is the bad data and see what type of check has failed. Another thing that is used quite extensively is custom validation. So we can define this function here of a certain type of custom check that is harder to incorporate maybe within the base model. And using this validator function, let's say for the garage area, we are expecting it to be greater than 1,000. By using this validator decorator, inserting the field name, we can check that it is actually greater than 1,000. And if we get anything bigger than that, it will break. Cool. I think we don't have time for the exercise. There's only 6 minutes left. So what we can do is, if you have any questions at all about any of the subjects or tools that I've mentioned here, now will be a good time. Yeah.
I have a question from Great Expectations. I think the last method you showed was check the most values are in this list.
Yeah.
What is the definition of most? Is it like 60%, 80%?
I think it's probably the mode. So the most common value.
It was a list of values, so there's just one mode. But
Yeah, so it's saying the mode has to be one of these values.
Oh,
Any other questions? Yeah.
Great expectations. If I want to support a development or a production separation, I see you're saving the expectations JSON file.
Yeah.
Is it a matter of creating a great expectations in it in each environment and then simply committing the expectations JSON, saving it one and then learning from the other?
I think the way I would do it is create different data context for each environment. And yeah, I would create an expectation suite in the dev environment and then transfer it, like send it over to the production one. But the data contexts have to be different because you're also defining different data sources probably and so on. So yeah, that's the way I would do it. Yep.
How do you validate that your retracted validation rules are sufficient for robust deployment?
It's a good question. I think it's a matter of trial and error. I think you start with a set of like rules or logics that you have either from domain knowledge or by profiling your data either automatically or manually. And then as you move on, let's say you're building a product, you will probably encounter problems. You will probably, I don't know, have null values in your gender column. So you will have to put a check in place if you haven't had one already. So I think it's an iterative process of trial and error until you get it right. Yeah, you'll never get it right the first time. Yep.
When would I use like great expectations over
I think Great Expectations has really nice profiling tools. If you, let's say, you're handed over like a data set you've never seen before, you can scan it through with an automatic profiler, which will suggest maybe even sometimes even hundreds or thousands of expectations you can implement with a few lines of code. I think the other factor to consider, as I've said before, is how big is the community. So the community for Pydantic is quite big, and there are many tools, pretty complicated ones that are using Pydantic. And yeah, and if you go to the GitHub page, there are millions of people, not millions, but a lot of people who are asking questions that are problems you'll probably encounter if you try to use it too. So I think, yeah, those are the two main kind of like reasons. Any other questions? No? Okay. Thank you for your time. I hope you enjoyed it.